we're going to focus on this turning points, idea of finding turning points in functions, and we'll talk about what we mean by that and how you calculate it, and a particular rule that we're going to need to find the turning points in certain types of functions. Let's look back at this function here that we've just been looking at. If I look at this function, this sine wave that looks like this, a turning point is meant by a point at which the function, the gradient of the function, turns through a zero, like this. So it tends to be associated with maximum values. Or, if we look at this part of the function down here, where it's turning from a negative gradient to a positive gradient, turning through that negative to positive, again it goes through a point where the gradient is zero, and that's associated with a minimum. So we can find maximum and minimum values of functions, and I think I sort of mentioned this briefly when we first started talking about these. We can find maximum and minimum values of functions using calculus, because what we do is we differentiate the function, and that tells us a function to tell us the gradient of it, and then we look for points at which that gradient drops to zero, here and here. The differential won't tell us whether we're looking at a maximum or a minimum, but it will tell us it's a turning point. So we call these turning points. And so what we're going to do is look at a way of finding out what those turning points are, but also where those turning points are. Where is this turning point of this function? At what point on this axis is this turning point? At what point is that turning point? What value of x, where we get those maximum minimum values? And more than that, once we've got that, well, if there is a turning point at this point, what is the value of that maximum? Well, we know what it is in this case, it's 5. What is the maximum value in this function? We know in this case it's 5. So we don't necessarily, in this particular type of function, need to differentiate to tell us that the maximum value is 5, because that's the amplitude. And we're going to need a way to determine whether or not what we've found is a maximum or a minimum. So that's what we're going to look at. And there's a little recipe that we go through. And here it is. To finding the turning point, let's look at it, and then you can write it down. I'll pause while you write it down. So to find the turning point, we differentiate it, because that tells us a function that will give us the gradient. And then we let that differential equal 0, because that's when the gradient is 0. So we find this differential and then find where that function equals 0. So we let the differential equal 0, and that will give us a little equation which we can solve for x. And that's where the problems might start, because solving that equation involves algebra. And remember, the problems with calculus is not the calculus, it's the algebra. So we're going to have to solve an equation, and then what we do is we use the second differential to identify the nature of the turning point. The second differential tells us the rate of change of the rate of change. So if we look back at this function we were just looking at here, if the rate of change of the gradient function is turning from positive to negative, that's a maximum. So if we find the second differential, the rate of change of the gradient function, and find that it's going negative, positive to negative, then that means it's a maximum. If we look at the second differential and we find it's going from negative to positive, so it's a positive gradient, then that means it's a minimum. So we can use that, and we'll look at an example to help us find out the nature of the turning point by finding the second differential. And then finally, once we've got our values of x, where the turning points are, in other words, we can then substitute those values of x back into the original function to find those maximum values, y. So that's the recipe, that's what we do, 4-step program, okay? So make a note of them. Are you feeling positive or negative about this? If you're feeling positive, that means you've got a positive gradient when you find the second differential, and that's associated with a minimum. So that's that little aid memoir. If you're feeling negative about this whole thing, which none of you hopefully are, that's telling you that if the second differential is negative, that's associated with a positive, maximum rather, okay? So a negative gradient gives us a maximum value, a positive gradient gives us a minimum value, and that's the way to sort of remember it. So if you want to put that down, you can. So let's use these steps then in an example, and what I'm going to do is use the example that we've used already, which is this function y equals 5 sine 3x. So we know what the maximums are going to be. I'm more interested in where are those maximum values. At what point along the x-axis do you get those maximum values? Here is the function y equals 5 sine 3x. Well, I know that it's going to have an amplitude of 5, so I know they're going to appear there. But the point is, it's not what is this value of that, but where is it? You know, when does it hit this point? And when does it hit this point? What are those x values? I can zoom in using autograph and come up with a value. The more I zoom, the better. But let's use differential calculus to do it. And we're going to follow those 4 steps. So, y equals 5 sine 3x is our function. Step 1. Differentiate it. Done that already, so write down the differential. Let's use the notation dy by dx equals, and then just write down for me what that differential is. Hopefully you got 15 cos 3x. Step 2. I'm interested in when this equals 0. So let the differential equal 0. So 15 cos 3x equals 0. And now I've got to solve that. I've got to find x. First of all, the fact that the right-hand side is 0 is often very helpful, because I can multiply or divide by anything I like, and it will always be 0. So if I have the whole thing, the cos 3x is times by 15, if I divided that by 15, divide by 15, they would cancel. And 0 divided by 15 is still 0. So if you've got anything multiplied or divided by the thing you're after, the function that you're interested in, they disappear because the right-hand side is 0. So cos 3x equals 0. Dividing both sides by 15. If you want to make that little note to remind you. And now I want to find the value of x, so I'm after the angle whose cosine is 3x. So 3x equals cos to the minus 1 of 0. And now we look at what cos to the minus 1 of 0 is, but if we can visualize a cosine function, you might be able to tell me what the cosine of 0 is. If I'd asked you to sketch not the sine wave at the beginning but the cosine wave, that would have started at 1. So the cosine of 0, check on your calculator, the angle whose cosine is 0 is 1. So 3x equals 1. If in doubt, do it on your calculator, and check you're in radians. So now x equals 3. Sorry, x equals a third. Divide both sides by 3. Done. Let's look back at the function. When x equals a third, yeah, so cos the minus 1 of 0 is pi over 2. So x equals pi over 6, dividing both sides by 3. So x equals, what's pi divided by 6? Bobby? 0.52. Okay. So x equals around about 0.52. Yeah. Cos of 0 minus 1 of 0 is 0. Yeah, I was thinking of cos of 0, which is 1. Yeah. Okay. I knew immediately it was wrong, because what I do now, of course, is I've got my value of x equals 0.52. I go back to my function and see where it actually is. And about 0.52, that's where it is. So if I'd zoomed in, that looks as though it's about right, doesn't it? About 0.52. And so we're sort of confirming it's right by using autographs. So we get a value of x, a constant at 0.52. The problems, that's a maximum value. Well, we're going to confirm that in a minute. So that's this point here. But what about this point here? And so there are others. There are lots of different points at which the cosine function can occur, can give us a cosine which is a maximum point, or a point at which we get zeros, a turning point in other words. So we have to think about the cosine wave.
Is the cosine wave then not considered in an equal way, then it wouldn't matter where you sit, whether it be to the top or the bottom, because all this will get the same x.
So if we look at a cosine wave, there are other points at which this sort of, we get this zero. Points at which we have to remember the points at which the cosine, the angle whose cosine is 0. So the angle whose cosine is 0, this is the cosine. So the angle whose cosine is 0 is there, that's one. Here's another one, here's another one. These are all the angles at which the cosine equals 0. And so we found the first one, and if we look at the wave, this is one complete turn. From here to here is one complete turn. And what's one complete turn in terms of radians? 2 pi. So I know that must be pi, and that must be pi over 2, which confirms what we were just saying. That's the point at which our calculator gave us the angle whose cosine was 0. But the next one occurs at this point. And so what's that point? Three pi over 2, isn't it? So there's another point at which the cosine is 0 at that point there, so at 3 pi over 2. So I could have taken this as well, 3 pi over 2. I've added pi, effectively. And if I carry on with my curve, there are further points. What's this one here? If I add another pi to 3 pi over 2, I get 4 pi over 2, which is this one, 5 pi over 2. And 7 pi over 2. Every time we add pi, we get another point at which the cosine of the angle is 0. So 3 pi over 2 is the next one. I could have added pi again to get 5 pi over 2. At each of those points, I get the cosine equal to 0. In other words, I get a maximum value on this curve here. I get a maximum there. Pi later, I get one there, and so on. Often you're after the first maximum, but you could be after others. So you need to think then about what the how I get my successive ones. And to do that, you need to think about the function you're looking at. The first one occurs at pi over 2, the next one at 3 pi over 2, and so on. Yeah. Just to recap, make sure we're not losing our track here, because I've sort of gone off on a bit of a tangent. So what are we doing? We're after this finding the positions at which we get this maximum value. Step 1, differentiate. Step 2, let that equal to 0, which gets us to here. 3x equals the angle whose cosine is 0. And then we discuss the first one, because the calculator gives us that. That always gives us the first one. But then we may think about, in terms of finding successive ones, by thinking about the actual curve that's involved here. So pi over 2, and then so on. So we've got our value, x equals 0.52. And so we found the point at which we get this maximum value. Step 3 was to confirm whether or not this is a maximum or a minimum by finding the second differential. d2y by dx squared. That's the notation for the second differential. d2y by dx squared, pardon me. The third differential, d3y by dx cubed, and so on. This is a notation. It does not mean d squared times y divided by d times x squared. It's a notation to mean the second differential. And so to get this, we just take our differential. So let's write that down. dy by dx was 15 cosine 3x. So now we've got to differentiate that to get, again, to get the second differential. Same procedure. If we look at the table of differentials for the cosine one, again, you bring the 3 out, times it by the number in front, so that's 3 times 15 is 45. But now, the cosine changes to a minus sign, so minus sine 3x. That's the second differential. Now, we're interested only in whether that's positive or negative when x equals whatever value we have, 0.52. So is this positive or negative when x equals 0.52? In other words, is this a maximum or a minimum? So we put in the value of x, 0.52. d2y by dx squared equals minus 45 sine of 3 times 0.52. So now I get my calculator out, check I'm in radians, plug it in. And I'm not interested in the value, just is it positive or negative. Negative, okay. Just as a matter of interest, what is it? Sorry, who's talked? So negative 44.99, it's negative in other words. And if we look back at our list, negative is associated with a maximum. Because the second differential is going from a positive gradient to a negative gradient, so it's going negative. So this is associated with a maximum. So we've got a maximum value when x equals 0.52. It's negative. That's step 3. Step 4, we hardly need to do step 4 in this case because we know the value of the maximum is going to be 5, but let's confirm it's 5. So the final step, step 4, put our value of x back into the original function. So what is the original function? Y equals 5 sine 3x. And put in our value of x equals to 0.52. We're going to have rounding issues here, so we might not get exactly 5. 5 sine 3 times 0.52. So we put that into our calculator, checking we're in radians. And it gives us around about 5. 5 to one significant figure, certainly. Confirming that we've got a maximum value of 5 at 0.52. So let's just confirm what's gone on here. We've taken our original function. Here it is, y equals 5 sine 3x. We differentiate it. We let that differential equal 0. And then we find out the value of x, which gives us that, which is the first one we come across is this one. So I know that the gradient drops to 0 at that point. So we've got a maximum or a minimum. If I've got a trigonometric function, if my differential turns out to be a trigonometric function, which this is, then I instantly think to myself, well, actually, I've got a repeating pattern here. So I'm going to have more than one point at which the differential drops to 0. And so I might well need to think more than one. But in this case, I'm just interested in the first point. So I know the first time it reaches 0 is when x equals 0.52. Next thing I do, step 3, is I differentiate it again to find out whether or not this point is a maximum or a minimum. So I just find the second differential, find out whether that's positive or negative, and if it's negative, which it is, it turns out to be a maximum. So I've confirmed that this is a maximum, and then finally I put my value of x, 0.52, back into the original function so you can find the value of that maximum, which is 5. Done. Okay? So